thanks a lot for the invitation to be here.
Wait, if you want to
There's a present. Okay,
yes,
great,
of
thank you. Okay. Okay, yeah, thanks so much for the invitation to come here. I really love coming to Princeton every time. Basically, I'll try to give a little bit of an overview of the sort of the different phases that we observe in twisted bilayer graphene. And really, the talk is going to be, I mean, I have 2 lectures, right? So it's going to be basically 2 hours, over which I will try to cover most of those phases. Of course, correlated insulators, impermeable surface resets, symmetry breaking, then also reentrant correlated insulators in extremely high fields, churn insulators, orbital magnets, superconductivity, Josephson junctions, and strange metal phases. Really, so interrupt me anytime, ask me any questions. So I think I have really enough time to go through this, even with interruptions. And before starting with the physics, really just a little bit of introduction of who we are. So we were a group in IGFO in Barcelona for the last 5 years. And recently we moved to LMU in Munich, where we are already setting up our operation. We are also part of the Munich Quantum Valley and Munich Center of Quantum Science and Technology in Munich. So there's really like a bigger operation built up right now to study quantum materials. Also, I'm extremely happy for the collaborators that we had over the years. In particular, also here in Princeton, so we collaborate a lot with Andre Bernovic, Biao, and other people who work in the theoretical aspects of twisted bilayer graphene. Also, I'm very happy to have theoretical collaborations, for example, with Elizondo, Felix Baumberg in Geneva, and I will show some of their data today as well. And before again going to the physics, also because we're starting up our group right now in Munich, so we have also a lot of positions. So if you know anybody who's interested, so please spread the word. Okay, and so starting with the physics now. So as you know, so in 2018, basically big splash happened. So before 2018, graphene was considered to be a rather boring material. So everything was explained by a single particle picture, except if you would maybe bring the material to extremely high magnetic fields where fraction quantum Hall was observed, etc. But sort of in zero field, it was really mostly described as a single particle picture. And when we talk to people like from the comparative community and correlated electron community, they all would say that this is kind of a boring material. And this really changed when Pablo Carrero discovered these twisted bilayer graphene phases, correlated insulators, superconductivity, and so on. And of course, now we know that there are many other phases also in this material, such as orbital magnetism, trivial topological states, churn bands, etc., and very likely strange metal phase. And what's really important about this, so there has been a huge development over the last 4 years. There has been a lot of experimental work by now, but I think if you talk to anybody really in detail about what is the exact nature, what is sort of the exact ground state that we try to understand in the system, this is still like not fully understood. So there's a lot of debate still. And I think really what I want to emphasize here, the field is in its very beginning, and I think we're still there's still a lot of unsolved problems and I think that makes the field still exciting, that we can still try to do more experiments and theory to understand all those phases. And in this regard, I want to say that of course some phases are better understood. So for example, I think the topological and orbital magnetic phases, those are more or less understood. So there's really has been a lot of progress in the last couple of years. That concerns correlated insulators also to a bigger degree. But what are the rather still big open questions is, for example, the nature of superconductivity. So it seems to be some sort of unconventional superconducting phase. So there have been many groups also here, Ali Yazdani group, who has shown that this is more likely a ID wave or like a nodal superconducting gap that they observe here. But in principle, the exact nature of the ground state, this will probably take us a couple more years to understand. And of course, also the strange metal phase, which is sort of a topic of our debate right now as well. Okay, and so really sorry for the deeper introduction here, but really just want to cover 2 slides of how these devices are actually really made and what really made these devices really possible. And really, it all began with in the group of Philip Kim back then in around 2010, where people realized that you can stack two-dimensional materials one on top of another. And of course, this happened all with like a simple Scotch tape trick where you deposit 2D materials in a single layer form onto substrates. And then people have figured out really how to pick up these materials and stamp these materials one on top of one another. And really, surprisingly, we were able to make these van der Waals heterostructures. We could really pair any type of two-dimensional material species and assemble them together. Surprisingly, also the interfaces were extremely good. I mean, I think if you are familiar with other growth techniques to grow heterostructures, etc., this technique sounds extremely simple, right? But really, it was a big surprise to find interfaces between the two-dimensional materials that are so clean and where you really have perfect hybridization of those materials without trapping too much of disorder that can kill all of the physics here. And of course, the main principle here that made this field possible was, of course, that you can also orient the two-dimensional materials in any configuration that you like, and you can create these Maurice superlattices. And I really want to contrast this for a second to why this is so special. And it's so special because people were growing heterostructures really for decades. So I think, as you know, so for example, gallium arsenide started like in the 80s, etc., and people were spending decades and decades to grow heterostructures between gallium arsenide. And of course, also for complex oxides, you can do the same trick. And usually, the best sort of grow technique in this field is molecular beam physics. And molecular beam physics works in the following way: that you sprinkle individual atoms, very dilute atomic species, that you sprinkle atom by atom on a given substrate. And because you start up with individual atoms, these atoms, when they assemble on a surface, they inherit the crystallographic orientation of the underlying substrate. And so basically, you can grow different species of different elements one on top of another, but you always align the crystallographic orientation of these species with respect to the pattern substrate. So crystallographic orientation is not possible here. And this is really different here for for twisted Bilayer graphene and for van der Waals heterostructures, where we start up with preformed two-dimensional crystals. And because we have these preformed two-dimensional crystals, we can really orient them as we like. We can assemble them in any crystallographic orientation that we want. And only this sort of assembly process allows us to really control the crystallographic orientation here and to induce Maurice superlattices. Okay, and really, as you've heard from all the other talks, of course, and also like the name of the school is, of course, the magic happens because of these flat bands that are created in twisted Bilayer graphene. So when you rotate two layers of graphene at exactly the magic angle condition of 1.1 degrees, we end up with these extremely flat bands. So, and this is basically a typical Bishop-McDonald model calculation with strain and corrugations inside the Moravian itself. And we usually find extremely flat bands in the order of 10 MeV. And these flat bands are separated by larger band gaps of around 40 MeV to higher order dispersive bands. And so really the starting point to think about the strong correlations in these materials is really given by these flat bands, because if you look at the kinetic energy in such a flat band, it really diverges to zero. So the electrons are basically stop moving, they're very slow. And the dominant energy in your Hamiltonian becomes the interaction energy. And this is really where all the physics starts here. And of course, the second main ingredient of these flat bands is, of course, the non-trivial topological properties. So as I will discuss later on, of course, now we know from a lot of theory work and also from supporting experiments that if you start analyzing the sort of winding numbers in the newly formed billion zones, in these mini billion zones that are formed by twisting these two graphene layers, you find that these mini billion zones have non-zero helicities of 2 and -2, in contrast to single layer graphene, which has a overall helicity of 0. And this sort of fact leads to it's impossible to find localized linear functions in such a system. And basically, what you end up with, Chern bands where electrons are basically not localized at the lattice site. And in principle, a priori, these flat bands basically are formed out of 8 degenerate Chern bands, and I will talk a little bit more in detail later about this. But these 8 Chern bands are exactly degenerate. They have exactly the same energy, so the total Chern number in a single particle picture is just 0. But keep in mind, indeed, so we not only deal with flat bands here, with very strong interaction energies, but also with topological nature of these bands. And really, this is a unique system. So I think, correct me if I'm wrong, but I think this is the first system that has really strong correlations and topology at the same time. And so this really opens up a sort of a new sort of direction of physics where you can study strongly correlated electrons in a topological system. And really, just before I go into more detail, just want to show you immediately a couple of sort of measurements of this twisted bilayer graphene system. So this is, for example, STM measurements of the topography of a typically S-fabricated twisted bilayer graphene device. Of course, STM is now one of the most sort of successful techniques in the study of these materials, as is done, of course, by Ali Azdani here also in Princeton. But really, what I really want to emphasize, just to give you some intuitive understanding of this, is really that this is sort of a height map of a 250 by 250 nanometer sheet of twisted bilayer graphene, and the individual sort of lattice sites that you see here, those are not individual atoms, but those are really these moire patterns. Those are really these 8A lattice sites in the moire pattern. And really, it seems to be possible to make large-scale clean devices, whereas, of course, we still suffer from a non-perfect fabrication protocol. But in principle, if you make enough devices, you always find like larger areas which are extremely homogeneous. And another thing which I also want to show immediately is also sort of measurements of the band structure. So, of course, one of the sort of main tools to extract band structures from materials is, of course, ARPAS. So it is possible to do ARPAS on these materials. Of course, there are difficulties because it's nano ARPAS measurements, so the resolution is maybe not the best. You need extremely clean devices to extract some band structure. But nevertheless, it worked for a couple of devices around 1.3 degree twist angle. And you can see, so basically from the ARPAS measurements, we can already extract sort of a flat band and zone folding of the twisted bilayer graphene. So this is really where at zero energy we see sort of these cloud-like features. Of course, resolution is not the best, but you can already guess that there is a flat band here at zero energy. There are also band gaps formed to higher energy bands, and you also can see the zone foldings in the band structure here. And this is in principle exactly what you would expect from theoretical calculations, where really the band structure looks similar to the band structure of AB bilayer graphene, except that really the moire potential strongly normalizes the spectrum, forming these isolated flat bands close to zero energy. Yeah.
In the topography map, like how much variation does that color represent, and is that problematic for measurements?
Variation of what?
Sorry, the topography map.
Yeah. Yeah.
Variation in height.
Yeah.
Color. What does that correspond to?
So you mean so there's like a background. There's like a background variation, like a larger scale background variation here.
Yeah, exactly.
Yeah, so I mean, I'm not an STM, so this was done in cooperation with Neil and Alan and Leiden, so I'm not an STM person. But I guess there must be some STM people here who can explain you more. But as far as I understand, sort of, I mean, the substrate on which it all sits is not necessarily completely flat. So basically, the substrate on which the twisted bilayer graphene sits has maybe some height variation. But in principle, that should not affect the physics much at all. Yeah. Okay, so this is really just the introduction of twisted bilayer graphene, and then here I really also want to contrast it to other systems that have been found to exhibit very similar physics, right? So again, as said, we find all these phases in twisted bilayer graphene, and really what defines sort of the length fields and direction energies here is the moire superpotential, right? And so the moire superpotential is usually for magic and graphene is usually in the orders of 10 nanometers. So in fact, it's like 15 nanometers. And really, this length scale defines mostly the interaction energies, which therefore are in the orders of millielectron volts. And what's different here, for example, to systems that have been known also to exhibit sort of a similar zoo of electronic ground states, such as crystals, for example, like the cuprates or the iron pictides and so on. This is, of course, very tempting to compare these systems. But what's really different is that these are crystalline systems, and therefore the sort of lattice constant is much smaller, right? So the lattice constant of crystal is in the orders of angstroms, and therefore, like in a multi-insulating state in a cuprate, the interaction energies are basically defined also on that length scale, and therefore the interaction energies are much bigger. They're in the orders of electron volts. And of course, another system which was also famously demonstrated to have similar physics, of course, optical lattices. So those are basically artificially made materials, where atoms are trapped in standing waves of lasers. And really, if you compare this to optical lattices, the length scales are in the orders of micrometers, so they're much bigger, and therefore also the interaction energies are much smaller. So to perform these experiments, we need to basically cool them down to nanokelvin temperatures and so on to observe any of these phases. But of course, those are not the only differences that magic angle graphene offers. But there are really some novel control knobs that we can also apply here that are otherwise not possible in these other systems. So in principle, having this sort of new systems platform also opens up new possibilities of how to study the material. And one sort of immediate tuning knob that I want to show you is, of course, based on sort of the understanding of the Hubbard model that describes sort of the modern insulating phases here. And in the Hubbard model, typically the most important energy scales are of course the kinetic energy T that basically defines the hopping between two different lattice sites of electrons, and of course the interaction energy U, which basically is just the Coulomb energy if two electrons sit on one lattice site. Of course, this costs additional Coulomb energy. And so in principle, in the Hubbard model, all of the physics can be understood by sort of the relation between the hopping energy and the on-site energy U. And really, in twisted Bilayer graphene, we have now direct tuning knobs of both of these quantities. So first of all, if you look at sort of the calculation of the bandwidth of twisted Bilayer graphene, the bandwidth is a direct function of the twist angle. So basically, as I said, at exactly magic angle of 1.1 degrees, the band is the flattest. So there we have these 10 MeV bandwidth. This is really where the kinetic energy is the lowest. But whenever you tune out slightly a little bit away from the twist angle, from the magic angle, if you go, for example, so to 1.0 degrees or 1.2 degrees, etc., then the bandwidth dramatically increases. So at around 1.2, it's already 100 MeV. So in principle, you can tune directly the kinetic energy by basically tuning the twist angle. And this is really, if you look at many of the experiments right now, very often really to demonstrate the special physics that we observe at magic angle, we always like to make devices which are slightly away from it to really highlight the contrast in behavior. And the other thing, of course, the on-site energy U, this is also in principle very well controlled in the system. And this is due to the fact that because we assemble these van der Waals heterostructures, we can really place any type of dielectric environment to the material, and we can also place screening layers, metallic screening layers, very close to the twisted Bilayer graphene. And really, this sort of complex dielectric environment allows us to control interaction energies in the sample. And really, as you can then see, sort of the most important sort of criterion for forming a Mott insulator is the criteria that U versus T is much bigger than 1. So that basically interaction energy is much bigger than kinetic energy. And here, really, in these devices, we can control it. And really, neither of those sort of tuning knobs you have in crystals, neither you have them in optical lattices. So this is really some novelty here. And another thing is, of course, most of you know this, of course, but another thing is, of course, that we can control the carrier density in this material continuously. So this is, again, something you cannot do in crystals. You cannot do this in optical lattices. But because we have such a low carrier density system, we have these sort of capacitively arranged devices. We can control the Fermi energy throughout the flat band continuously. And we can really take in one device, without interruption, we can take carrier density controlled measurements and extract the phase diagrams basically continuously. And think about cuprates, for example. In order to extract a density dependent phase diagram, people needed to grow like 100 different crystals with 100 different doping levels, and then assemble phase diagrams really from those materials. And here it's possible really in a single shot if you want. Okay, so this is sort of the introduction, but let me now move over to sort of transport measurements. And really, I will start with a typical phase diagram that we obtain in these materials. And really what we measure is just resistance as a function of carrier density. Most of the time, most of the measurements you will see is just resistance or hole resistance as a function of carrier density. And when we measure the carrier density, we always like to normalize the carrier density to electrons or holes per unit cell. So basically a measurement like this, so this is Rxx as a function of n is the carrier density. Usually we can extract really the size of the Moiré unit cell from the devices, and we can basically relate this carrier density into filling factor. And filling factor means really just nothing else as 1 electron, 2 electrons, or 3 electrons per unit cell. And so what you can see in such a phase diagram is the following. So a red here, a red is high resistive regions. Dark blue is close to zero resistant regions. And basically, if you look at the phase diagram here, first, what you see is that at many of the integer fillings, so here at 1, 2, 3, we get highly resistive regions. And if you really look more carefully on these regions, those are really insulated regions, which show activated temperature events. So those regions are really understood as correlated insulators. So those are really these mud-like insulators where electrons localize on a lattice. Then looking further, as you can see, so very close to many of the insulated phases, we also observe dome-shaped regions of zero resistance, and those are really explained as the superconducting domes here. Here resistance really drops to zero, and as I will later on show, this has really all the attributes of superconductivity, including Fraunhofer interference pattern and coherent behavior of the superconducting state. Then moving on here, at a filling factor of 1, here we also observe a sort of magnetic behavior. This magnetic behavior shows up at a non-zero Rxy signal, so basically non-zero hole resistivity in a zero magnetic field. And furthermore, this non-zero hole resistivity also shows sort of hysteretic behavior, whether we sweep magnetic field up or down, which is really indicative of a typical sort of magnetic behavior of a magnetic state. And moreover, if you actually look closely, so the hole resistance that this magnetization corresponds to is very close to h over e squared. So really, it is tempting to believe that also the hole resistance here is actually quantized, and it's similar to anomalous quantum Hall effect. And indeed, some other groups, the group of David Goldhardt-Gordon and Andrea Young, they showed really that in the best case, in sort of a very clean device, these states can be also perfectly quantized. So that, therefore, it's not just a magnetic state, but it's a state with a magnetic bulk and edge states really similar to anomalous quantum Hall effect. These features of the orbital magnetism, they can also be traced to a higher magnetic field. So in particular, at higher magnetic field, if we applied several Tesla magnetic field, we can also see a much richer sort of magnetic features where we see basically Chern insulators appearing in the Landau Venn diagram. And last but not least, when we basically tuned in the middle of the band, so where everything behaved as a normal metal should, we also observed a strange metal behavior, which really exemplified itself as a linear temperature dependence, even down to the lowest magnetic field. So overall, really, I think when we started studying these devices, we were quite impressed by the richness of the phases that you can observe in one single device. Again, all of these phases are really produced in one single device, depending on the magnetic or electric field that you apply to the device. So you can tune between the different phases. And I think this really opens up new possibilities to study.
We saw yesterday this cascade picture as a function of the field. Should we see it also in the transport measurement? The cascade, the fact that we have the symmetry breaking between different flavors.
Yeah. So we see this in transport. Absolutely, and I will talk about this in more detail. Yeah.
But it's not something from this.
Which cascade are you mean?
I mean the fact that you have this breaking of different flavor symmetry.
Yeah.
The function of the filling.
No, we have.
So
I mean, you can see this.
Plot, can we see it? Or?
Yeah. So for example, here you can see it. But I will talk. I mean, actually, all of those phases, if you want, have something to do with the symmetry breaking. But I will go for each of the phase in more detail to also explain the symmetry breaking here. Any more questions?
I just want to ask, what's the difference between correlating to and tuning to here? I mean, both of them are correlated to
right? The difference is Chern number. A correlated, yeah.
But how do you think in an experiment that? I mean, you just using this of the lambda function.
Yeah. So I will exactly. So I will talk about this in much more detail. But yeah. So basically, in a Landau fan, a Chern number 0 is really has no slope. And a Chern number, depending on the Chern number, the slope is quantized basically.
In Jakob's slot,
yes,
they show some vertical.
Exactly. So basically, in other words, if I would take a magnetic field dependence of these features here, they would have no slope in the magnetic field. But I will, and so basically, for the rest of the talk, I will just go for all these phases in a little bit more detail, just to cover a little bit the ongoing sort of understanding of these phases. And so I will start basically with the correlated insulators, and really, as mentioned here, so when we started working on this field, so the first sort of feature that we were always looking for were the correlated insulators, and you can see from this basically from these transport measurements is if we measure resistance as a function of density, or in other words, as a function of filling factor, right? The features which are explained here by the single particle picture, basically by this band structure that I showed you in the beginning, by the flat bands and by the band gaps associated with that, are really just the features that appear at filling factor -4. This is when the flat band is completely empty. So this gap here is a single particle gap, and you can see the resistance goes here up to like mega ohms. So this is a really good insulating state, and really explained by single particle picture. Then if we move and fill up the bands, at one point we fill up the entire band, and we are ending up at the sort of other gap, which is at high at a filling factor of 4. So this is when the entire Moiré band is completely full, right? So this gap is also a single particle picture. Of course, at one point we sweep with the charge neutrality point. So at 0, we observe resistance peaks, which is also kind of explained by the single particle picture. And really everything else you see here, all the other features, they're completely unexpected. They were completely they're really direct sort of consequence of the strong correlated electronic correlations. And as you can see, so these resistance peaks that we observe here at 1, 2, 3, -1, -2, -3, they really appear at exactly integer filling. So exactly when we have 1 electron per unit cell, 2 electrons per unit cell, or 3 electrons per unit cell. And this is really already very indicative of what's going on in the system. And really, so the picture, and of course, we can also check, are those really insulators? So typically in transport, we tend to underestimate sort of insulating phases, because transport likes to shorten out gaps. So in STM, for example, typically you find a much bigger gaps in their measurements. But what we do typically really to identify a transport gap in an experiment is we look at the temperature activation of it. So the resistance at low temperatures really just goes up exponentially. And this is how we know that we really are dealing with a gap here. And this is a typical measurement of all the sort of integer fillings that I showed you before. So we sit at one of those resistance peaks, and we just measure the temperature dependence. And instead of resistance, we plot here conductance, and instead of temperature, we plot 1/T. So, and basically what these linear fits to these lines are basically really just giving us this temperature activated exponential behavior. And really from these fits, we can start extracting real gaps, real energy gaps. And what we find is that really most of these states are insulating with a gap size in the orders of 1 MeV. So those gaps are not as big as you would expect, for example, for the Cook rates. There, the gaps are much bigger. But still, I think 1 MeV is definitely a sizable enough gap that to deal with. I want to also mention that from STM, the gap sizes that they extract are in the orders of 25 MeV. So if you basically really want to know the real magnitude of the gap, it's more closer to 25 MeV, and transport really underestimates these gaps. So, and really, how do we understand these phases is really, again, going back to the Hubbard model. So again, in this picture that we have sort of different lattice sites, and we have hopping parameters T, and we have on-site energy U. So as you can imagine, if you have a partially filled band, so if you look at sort of really just the band structure, and you have a partially filled band where really the different lattice sites are not fully occupied, and the electrons can really hop to free neighboring sites without ever paying any Coulomb energy, right? In this state, in a partially filled band, we just have an insulating state, metallic state, and really nothing is affecting the metallic state here. Really, the problems occur when we start filling at 1, 2, or 3 electrons per unit cell, where really the electrons, when they hop to they don't find free neighboring lattice sites, and the only way for them to go through the lattice is really to pay the Coulomb energy and to occupy a neighboring lattice site with two or more electrons. And this is really when these mod-insulating insulators appear. This is really, again, this only occurs when the kinetic energy is much smaller than the Coulomb energy. And really, in such a situation, the system polarizes the band. It opens up a band gap. And really, otherwise, sort of metallic band polarizes into the bands and forms an energy gap. And so this is sort of then a mod insulator. And as you can already see, as you know from Philip's talk yesterday, we have here a fourfold degeneracy. We have spin and valley degrees of freedom in the system. What this sort of opening of the mod gap immediately also does is polarizes and breaks symmetries in the band. So and of course you can immediately sort of imagine that sort of the simplest possible scenario would be that just a gap at half filling would basically break either valley or spin, in which case you would immediately get a ferromagnet or a valley ferromagnet, right? So this is immediately how you can understand how magnetism sort of occurs in the system. But of course, because it's SU4 phase space, right? Of course, it's sort of symmetry breaking in the SU4 phase space. So we typically don't get sort of a simple valley or a simple spin polarization, but it's sort of symmetry breaking in the SU4 space, and we get sort of any sort of combination of spin and valley breaking in the system. But this gives you, I think, immediate sort of intuition where the magnetism actually comes from in the system. And really, overall, really, this is sort of the nature of the symmetry breaking. So whenever we fill 1, 2, or 3 electrons per unit cell, we form these mod insulators, and we immediately polarize the band and break some symmetries. Okay, and the other thing which happens in the system when we also basically form these correlated insulators is that also we observe interaction-driven reconstruction of the Fermi surface. So basically, every time we fill 1, 2, or 3 electrons per unit cell, we form a new Fermi surface, and we basically reset the carrier density of available electrons to 0. And this you can see, for example, from these Hall measurements. So a Hall density is basically a measurement of the free carriers in the system. And of course, we can measure the free carriers of the system as a function of the total carriers, if you want, right? And you can see sort of these linear lines here, which you can fit close to 0. This is really something which is just the Hall effect. So the Hall effect gives you sort of a linear dependence of the carrier density to the normal density here. As you can see, so whenever we fill up, we cross half filling here, so -2 or 2, this carrier density is reset back to 0. And we start basically counting electrons from scratch. So that means that these electrons, whenever we form the correlated insulators, we form new Fermi surfaces, and we have Hall density resets, and we basically start from a new band if you want. And this is really what also then was explained by these Dirac revivals. I think Philip talked about this, maybe also Amir talked about this, I don't know. But basically, the sort of explanation that people have found, this is a phenomenological explanation, to explain sort of this reset of the Hall density is that really whenever you basically fill up all the different flavors together, starting from 0, and then at exactly 1 integer filling, you empty all the other flavors and you fill up completely only one of the flavors. And so basically you end up with this sort of cascade of phase transitions where basically every time you cross one of the integer fillings, you end up with a new Fermi surface, and you basically end up with a different sort of flavor that is occupied in the system. It's basically starting from one flavor which is occupied, and in the end, at filling factor 3, you get 3 flavors which are occupied. So it's really rich sort of sequence of phase transitions that's going on. And also, in order to sort of quantify this symmetry breaking, I also want to show you some Landau fan measurements that we do in the system. So basically, Landau fans, this is basically when we measure the resistance as a function of a particular magnetic field. So we apply several Tesla typically to induce really strong Landau levels and observe Shoemaker-Haas oscillations. And what you can see here from measurements like that is that you see a lot of linear diagonal lines here that appears in the system. And so each of those diagonal lines really are just Landau levels that we can trace. And these Landau levels really, if you sort of look at sort of the filling, the number of electrons that can go into a Landau level, this is really defined by the sort of the orbit in a Landau level. And you basically, if you compare it to sort of the magnetic field that is needed to create these Landau level orbits, you will find that each Landau level is exactly linear in the N and B phase diagram. So if you look at sort of the B and carrier density phase diagram, each Landau level appears just on a linear trajectory. So what we can do with data like that is we can then just start counting the Landau levels that we see. And looking at the Landau levels from charge neutrality, the typical sequence is that it starts with a Landau level with a degeneracy of 4, 8, 12, 16. So that means that all of the Landau levels are basically occupied with 4 electrons, so they're fourfold degenerate. And that means basically that spin and Belli degrees of freedoms are not broken. So it means it's really just the same symmetry non-broken state as a normal violation. But when we go to the filling factor 2 here, for example, we start seeing a different sequence. So we start seeing a sequence of 2, 4, 6, and 8. So it's now a twofold degenerate Landau level, where 2 electrons basically occupy each Landau level. And that means that some symmetry has been broken here. So that means that either value or spin or any other sort of combination of the symmetries has been broken here. And of course, we can repeat that trick. So here at -3, we see that the degeneracy, in some devices, we also seen that the degeneracy at a filling factor 3 is also lifted, completely lifted, so it's non-degenerate, so it's really just 1 electron bringing itself. So this is one way how to quantify the symmetry breaking that we see here is really by looking at the Landau levels and extracting the symmetry breaking from here. So this is really direct evidence of the SU4 symmetry breaking. Yeah.
Is it 2 along 0? So yeah.
Yes,
so,
I think there's more going on here.
No. So yeah.
Yeah. So this -2 we don't understand it.
Okay.
Yeah. So that's also other groups see that -2.
Yeah.
It starts with -2 and then it goes fourfold degenerate. It's a little bit
Interesting.
yeah. And I want to say also one thing we probably notice here is also that the Landau levels really go into only one direction. So except that charge neutrality goes in both directions, right, in the electron side and the hole side. But you can see, so here at filling factor 2 and here at filling factor -2, the Landau fan evolves only in one direction. And this is a little bit strange because in principle you have Fermi surfaces in both directions. You have Fermi surfaces in the hole and electron direction. And really, this is again something which can be explained by this phenomenological model of the Dirac revivals. If you look at how the bands are filled here, you would really only expect the sort of the different degenerate bands only in sort of one direction of the sort of doping that you apply to. And another consequence, this is just, of course, there's like, I know that under Bernovic and Biaur are working also on some theories which basically show clearly that the electrons on the doped side are much lighter than the electrons on the hole doped side. There's really like a heavy fermion sort of heavy fermion sitting on the hole doped side of these integer fillings that basically prohibit you to see strongly developed Schrödinger oscillations. Okay, so all right. With this, I want to shift a little bit gears. So I want to also immediately show you something which happens at high magnetic field. So this is work which we've done with Andre and Jonah, who's here. Hey. So basically, what we realized in discussions with the Princeton guys here is that these when you apply really high magnetic fields, of course, your bands break up into Landau levels. And in particular, in a system like that, twisted Bilayer graphene, you have sort of the unit cell of the carbon of the single layer graphene, but you also have, of course, these Mori unit cells. And of course, when you deal with large supercells like that, you also observe some Hofstadter butterflies, where basically your Landau levels break out into fractal patterns, and they basically sort of define your transport properties. And those are calculations done with Jonah. So basically where they looked at sort of, so this is energy versus magnetic field. And they looked basically in the evolution of the Hofstadter spectrum in magnetic field. And what we realized is that really, funnily, what happens at exactly flux of 2 pi through a unit cell is that the magnetic field of a 2 pi 2 pi magnetic field basically is almost the same thing as a zero magnetic field. So basically, your Landau levels, they again basically merge into one single band, and your band becomes again flat, like it was basically unaffected by a magnetic field. And this really happens at exactly 2 pi of magnetic field, which in twisted Bilayer graphene corresponds to 30 Tesla. So we thought 30 Tesla, this sounds a little bit high, but in principle, this is doable. So and we really did the experiment. So we took our devices to a high magnetic field lab, and we really applied a magnetic field of 30 plus 30.5 Tesla across the device, and really 30 plus Tesla corresponds to 2 pi flux through one Mori unit cell. And what happens is really the following: is that really if you look at sort of the magnetic field diagram as a function of carrier density, so here at zero field. And close to zero field, we observe this strong correlated insulator. This is this red region. Then if we trace this correlated insulator, it would really disappear. So there would be no signature of any sort of flat band again in the system. So the system would be broken up into Landau levels, and really close to this 2 pi flux. We saw exactly in a similar fashion as this phase appeared at zero field, reappear again in 2 pi flux. And this is the system here at 30 Tesla is similarly quantized. So we observe the same sort of quantum Hall features as we observe close to zero field. And also here in this sort of larger map, you can see that really the blue line is the sort of phase diagram. The blue line is the trace at zero field, and the red trace here is the trace at 30 Tesla. So really the same features reappear. And in other words, what this means is that really, if you, I mean, people like to consider new flatbed systems. People like to make new devices and create flatbed systems by device engineering. But really, also just by looking at sort of things like that, by applying magnetic fields and bringing it to high magnetic fields, you can basically end up with a new set of flat bands that can host very similar physics, but now with the addition that it's in 30 Tesla magnetic field. Yeah.
Why the superconductor is not real?
Yeah, exactly. So, and then of course, I mean, we were much more interested about superconductivity re-entering at 30 Tesla. So I think, yeah, superconductivity existing at 30 Tesla, that would be a really big deal. That would be, that's of course sort of what we're still hoping for to see. In these experiments, it's really hard to really align your device. So if you get a little bit of sort of non-alignment, that would mean that, for example, you get a slight parallel field, which would entirely kill the superconductor as well. The other thing is twist angle disorder in magnetic field. So would translate here into a sort of magnetic field disorder. So that would also might obscure things. So in principle, we after doing this experiment, we're still hopeful that maybe someday we can see re-entrant superconductivity. This is on our bucket list, but But again, this shows you, as you say, this is exactly how we thought about it. This is basically a new flat band that you observed now at 30 Tesla, and we try to think of what sort of interesting physics we can do with it. Yeah. Yeah.
So this 2 pi once thing, is it a fixed point? Because it happens, if you look at your data, it happens at around 25. It starts at around the 25.
Yeah. So exactly. So as you, also like also the zero field correlated insulator that survives for 50 Tesla before it sort of dies. Again, there are 2 ways to think about it. So the reason why this insulator dies in magnetic field is either that you sort of close the sort of correlated insulator gap by sort of polarizing the spin there, or it is closed just because Landau levels start sort of interrupting it. You know, so that it's sort of the band in general polarized into Landau levels. And the same, but you can see the same thing happens here. But again, it's exactly symmetric. It's a symmetric problem. Also, the field at which it dies here in the negative direction is almost the same. You can see it's almost symmetric, right? Yeah. So
this one, because because I think theory predicts that 2 pi is an exact point, right?
Yeah, exactly. So just like a 0 is an exact point, that state, the flat band is at 0 and 2 pi. That's where it's exactly the flattest. But of course, when you start applying magnetic field, you don't kill it immediately, right? Yeah. So it needs it survives a certain magnetic field, right? Oh yeah.
So there's a plateau at the limit of 0.
Right. Oh, this one?
Yeah.
Were you one of the reviewers? No, this is not a real plateau. So this is not a real plateau. It's it's also not anywhere close to that you. And also this is RXX, right? So yeah. So this is I think in high field you see that this feature here is in general. I think our contacts were freezing out a little bit. You know, in high field your leads start also interfering. So high field measurements are complicated. Okay, so how much time do I still have?
10 per minute.
Okay, all right. Okay, and so basically the rest of this sort of lecture, I'll try to cover also some of the Chern insulator features and orbital magnetism. And again, this work was also done in collaboration with Andre, Biao, and Jonah. And really, sort of the basis of sort of this discussion about topological insulators here is just like in my introductory slide. So if you analyze basically the one-year function, if you analyze the brilliant zones and the helicity in the brilliant zones, then the theory colleagues immediately find that it's really hard to construct localized one-year function, and therefore the bands are described by non-localized Chern bands, right? And these Chern bands in all of sort of in the single particle picture are basically totally degenerate. So in principle, the total Chern number of these bands is exactly 0. The only thing that you then can do to actually show that these bands exist, you can try to break some symmetries. So for example, in order to lift these Dirac points here, you kind of can break either reversal, inversion or time reversal symmetry, so C2T symmetry. And then you can basically lift these Dirac bands, you can open up band gaps, and you can start polarizing these Chern bands. And then once these Chern bands are polarized, once they have different energies, etc., you can start seeing them also in transport measurements, and of course also in SDM measurements and so on. And so basically what analysis really shows you, without going too deep in a detail, is that really the ground state that you basically make, so the basis from which you can make up these ground states has basically 3 quantum numbers. This has basically the quantum numbers of spin, valley, and sublattice. And we can basically define that depending on the exact combination of spin, valley, and sublattice, we end up with 4 Chern bands, which have a Chern number of -1. We end up with 4 Chern bands, which have a Chern number of +1. So in total, all these Chern numbers cancel each other out. And really, the details here are the following: that really, for example, a spin up K prime, 3 sublattice has a Chern number of -1, and a spin up K and A sublattice has a Chern number of +1. And really, there were a lot of groups who have predicted sort of this topological features. And I think one way also to think about it, which I found very intuitive, is that really when you form these Murray superlattices, you also form these AA lattice sites also have a different height. So this is for example what you saw in the STM measurements, is that really these twisted bilayer graphene films are not exactly flat, but they really have this curvature in height also in the AA lattice sites. And previous experiments in single layer graphene shown you that really curvature in graphene is basically the same as a pseudomagnetic field. So there were studies by many STM groups, for example, who curved graphene and showed that really they see Landau level formation in these systems when strain is applied. And really another way to think about these Chern bands, I think, is also that you really deal with a system which has a net magnetic field, and these are basically the system breaks down into zero order Landau levels. Okay, and really what theory then predicted, so this is work by, again, by Yao and Andre, etc. So theory really predicted that in the magnetic field, these phases should be visible. So first and foremost, theory also predicted that at high magnetic fields, all of these sort of states that we are looking at should be valley polarized Chern bands. So valley polarized states, which basically just means that you have some sort of valley polarized state, as is shown here, where basically some of the valley is occupying a certain number of Chern bands, and the other valley has occupying one less Chern number than the other valley. And so these valley polarized states for each Chern number really should appear as these sort of Chern insulators in high magnetic field. And really, we have really done some experiments, and also I think the first experiment was here done by the Yazdani group by STM. So, but really, what happens if we start applying a high magnetic field to our devices is that we really start seeing these valley polarized states. In other words, the breaking of these Chern insulators into sort of these valley polarized states. And so what we've seen here, this is our XX measurement as a function of, again, perpendicular magnetic field and carrier density and filling factor. And in principle, these measurements look very similar to like the Landau fan diagrams, which we showed you, except that really now we don't have these sets of Landau levels, but we really have very well-defined sort of features where from a filling factor of 0, we get sort of Chern insulator with a Chern number 4. The Chern number, again, we can extract from the slope here. So the straight up formula dictates that the slope is directly proportional to the Chern number. Or, of course, we can also do Hall measurements on the same sort of set of devices. So here, this is Hall conductivity as a function of magnetic field. And we can also extract from the plateaus that we see in the states which Chern number they have. So here, starting from 0, we really have a Chern number of 4, and we also have a 4e squared over h plateau here. So this is really consistent with one another. And we can do, of course, the same thing from this Chern insulator from filling factor 1. It has a Chern number of 3. Filling factor 2 has a Chern number of 2. And so basically, really, this is a robust sequence of Chern insulators which we can really extract here. And so what we believe, which is going on here, so as I mentioned, we need to break some sort of symmetry in order to polarize these Chern bands to be able to observe this. Of course, in a high magnetic field, you naturally break time reversal symmetry. So I think that already stabilizes these states. So really, broken time reversal symmetry starts polarizing these insulators. Another, of course, possibility is that interactions by itself. So some of these Chern insulators we were able to trace to a very low field, to like 0.3 Tesla or so. Another possibility is that interactions by itself already start breaking some of these symmetries, and then we just need to really a small magnetic field to actually completely kill it.
Can you know by transport if this is a spin polarized or valley polarized?
No.
Okay.
I mean, okay, so let's put it this way. So these states here, they're matching really well with what's predicted from theory, and of course, this is a valley polarized state, right? What is a little bit more difficult, and I'll show this in a second, is what actually happens at zero field. There, the system is much more degenerate. As far as I understand from calculations, also the states are so close by one another, the different possible states, that it's really hard to tell which state necessarily wins. And also, I think at zero field, you might have some sort of domain wall structure, which prohibits you to see this in transport, and then you need to apply a field to actually polarize all these things in one direction. So,
but in high magnetic, it should be very polarized going to zero.
this is exactly. So I mean, this is. I think we're convinced that this is very polarized state in side field, right? Yeah. Is there anything else to say, or?
Yeah, for the
Yeah.
highest two number states.
Yeah. Yeah.
Is there any experimental proof for that?
Where there's yeah. So I mean, it's hard to experimentally have a smoking gun experiment that shows something is valley polarized. I think probably STM would be the best technique to do it, but I think that's also very challenging. In transport, yeah, I mean, in transport, I think Philip showed some tilted field measurements on quantum Hall yesterday. So I think this would be also some way to go to check that. So yeah,
Optics.
right. So I mean, like spin versus valley should behave different in tilted magnetic fields. Yeah.
For the lambda level for the electron, it shows that the concept here is around 3 Tesla.
Yeah.
And does it suggest that the mobility of the electron, the free electron in the Moray system is much lower than the typical Graphene system? Because
right,
you know,
it is lower. Yeah.
Okay.
Yeah. So one thing. One thing we noticed about the system is that even at the lowest temperatures, in the metallic state, it has kilo ohm resistances. And I will actually, when I talk about the strange metal, I will probably come back to that. Whereas if you look at the cleanest graphene samples, they might have they're almost close to zero ohms. They're almost ballistic systems, right? So for sure, the system has much lower mobility. Yeah. And this is, I think, this is related to the strong correlations. Yeah. Okay, and so exactly. So just to close off a little bit. So as I mentioned, so one possibility is that this is magnetic field is breaking the time reversal symmetry here. One possibility is that it's kind of done by interactions by itself. And so I think what we I'm going in the wrong direction. Okay. What we found in one device, this is actually the device which I showed you in the introduction, is that actually some of these Chern insulators, they can be traced down to zero field. So this is in particular here for the spilling factor 1. This is a Chern number of 3, as I showed you before. But if we trace it back down to 0, at one point it disappears, and we end up with a Chern number of -1 here at zero field. And so the signature of the Chern number -1 is again as a slope in the sort of ND phase space, like the Schroeder formula dictates. But also this state shows a sort of a non-zero magnetization in zero field. So the bottom line is this is really in contrast to sort of lambda level, which is really induced by magnetic field. But here we see this state really surviving the zero field, and it really shows magnetization in this RXY sort of measurements, which really is a zero field magnet. And so the ongoing sort of understanding is that really most, again, it's a SU4 sort of paramagnet, right? It's basically not entirely spin polarized or valley polarized, but it's some sort of combination state. And basically, if it, sort of one way to look at sort of the magnetization here is really to look at sort of valley polarized state, where really the magnetization doesn't come from the spin itself, but really about some sort of valley polarization, but where really the sort of a circular motion, which is given by the valley symmetry breaking here, induces a really strong magnetic field. So basically, what to summarize this sort of chapter here is that really what's really important to know is that the flat bands should really are topological non-trivial. By breaking some symmetries, we can actually polarize these Chern bands. And really, in many cases, at zero field, the symmetry breaking can give you also zero field magnets, or in other words, zero field Chern insulators, if you want. Yep. Okay. Oh, microphone.
Is there a way to probe the Chern number without looking at the slope of this lambda upper? Because
Yeah. So right. So in this case, it's almost quantized to h e over squared. So it's basically close to a anomalous quantum Hall
oh, I
effect.
see, so that's the cost.
And so there again, there are two groups who were able to show that this is perfectly quantized as well.
So strictly speaking, because the previous definition of Chern insulator, it seems to me, was always a zero field. So this is
Right.
the closest to that traditional.
Right. Right.
Question.
Yeah.
Why isn't magnitude must come on the orbital for speed?
Yeah. So okay. So was this time to do it? Yeah. Okay. Yeah. Let me show you this. Okay. So there's so we did also this collaboration with Elizondo. So there they have a scanning squid scanning technique, and they can really very sensitively image the magnetization in the spatial distribution of the magnetization of the device. So this is how magnetization looks like. So it really has a domain wall structure, and I will not go too much into detail here. But what they can do is, of course, they can also sense the magnitude of the magnetization. Okay, so in the magnitude of the magnetization here is almost like an order of magnitude bigger than what you would expect from a spin magnetization. In general, if you would do calculations on the orbital magnetization, it's usually like an order of magnitude bigger than what you would expect from just a spin magnetization. So, so what I'm saying is, it's not necessarily, so the zero field Chern insulators, it's not necessarily a valley polarized state that gives rise to it, but there is for sure a big orbital component to it. So I'm not able to say anything about the spin degree of freedom there, but I think it's clear that it has a large orbital component to it. Going back sort of again to theory, so I mean, just to really, this is sort of the last thing I'm going to say right now. So theorists, they, for example, predict for the state a partially intervalley coherent state. So this would be a state of this form. As you can see, so it's sort of a combination of valley and spin, etc. So these states might be really complicated. But what's also clear is that there will be an orbital component and a spin component to it. Okay, so I think with this, I'll wrap up the topic, and then the next I'll talk about superconductivity.
Thank you so much.
Here, but it's straight line. And whenever we see a Chern insulator, it would always have a slope. It's more like this lambda level here. It would always have a slope here. And so if you look at here, it's basically a Chern number.
And you see this reentrant for any feeding that you see correlated insulator? Yeah.
No. So this is exactly. So I mean, as you can see, so we see something at very strong feature at 2, maybe something at 3. So there's also like a little bit of a peak at 3. So the red line here.
Yeah.
But it's not exactly the same situation at a zero field. So it's a different. So also like if you talk to Jonah, if you do the calculations, these flat bands look different. So those are different. Those are different flat bands than a zero field.
I mean, what is the major difference essentially? Why?
Just as I mean, first of all, just the first of all, there's dispersion related. I mean, dispersion looks different, right? So it's like if you plot them out, they're not exactly the same. But the bandwidth is pretty much the same, right? It's very close. Yeah. The topology is a little bit different then. But okay, so I haven't shown this, but also like
the topology mean except Chern number, right? Because there's no Chern number for that.
There can be these small purple holes that I can talk
But yeah, is it this experiment? I think it's you're detecting that as a correlating, so it's not Chern.
exactly correlated. Yeah. But also I want to say that I had to stick that slide. Each integer filling at high field also has this new set of lambda levels. There's really like a new Fermi surface open at each filling. So it's also, and from this we can also deduce sort of the symmetry breaking of these things as well. They seem to be all like symmetry broken.
Yeah, so I have two questions. The first one is about the nature of the correlating system. Is it more like a modeling theory where there's strong localization that can see down certain set in the array, or more like a quantum fire magnet there that can all incinerate and there's like a
Right. So I think that's a very good question, because at the same time, right? I mean, we also have these topological bands. So I think for me, it took a while to wrap my head around of how you have perfectly localized electrons, and at the same time you have churn bands with delocalized electrons. So I think, right? I mean, because when I think about it, mod insulator is a perfectly localized system. Like every electron just sits in place, right? But at the same time, we have churn bands and we have delocalized electrons seemingly going all across the device, right? So how is that? I think Biao is the guy who we should be talking to about this. Yeah.
Yeah, it's, general picture is
Yeah.
if your orbitals are more delocalized,
Yeah.
then you prefer paramagnetic and it stays safely full magnetic.
Uh-huh.
Yeah, because your optical wave functions can be anti-symmetrical. It's being polarized in the same direction. Yeah, that's my very vague arguments.
Okay. So it's more like a
So yeah, for churn insulators, for churn bands, SLA topology give you some more delocalized orbitals.
Right.
So it prefers the paramagnetic state.
okay, yeah. So I guess it's then closer to the quantum Hall ferromagnet then.
Second question
Yeah.
is the anomalous Hall effect is it aligned with the substrate?
No. So we don't think it's aligned with the substrate. But so okay, so I have to say that when people say aligned or not aligned, it's like a quantum number. It's on or off, 1 or 0. But we know it's a function of twist angle, right? So your HBN is never completely aligned or completely misaligned. It always has a certain angle to your graphene. And even, huh? No, I mean, it was like something like 15 degrees or so. I mean, again, it's indirect, right? We look at the edges of the crystals, right? It's indirect. So we, even if you look at sort of the early on papers on Hofstadter butterfly, right? Or like this paper by Pablo on massive Dirac electrons, where they showed band gap opening in graphene on HBN, right? They've seen a band gap even like at 10 or 15 degrees away from full alignment. Yeah. So okay. So my answer is no, because and I think my sort of this is the device. Okay. So this is the same device that Ellie measured then with scanning squid. And my understanding is whether we see these anomalous quantum Hall effect features or not is depending on the sort of domain wall pattern that you get. So if your domain wall, so we saw the so you see the full device is magnetic, but we saw the transport signature, the anomalous quantum Hall, only for like one pair of contacts. Okay, so you need to get lucky that your domain walls really fall. Allow you to measure this, right?
Yeah. Saying like first equal solve.
I mean, exactly. So my personal belief, again, you need more statistics on this. My personal belief is that in principle, it should be there in every device, but in transport, we just don't necessarily see it all the time, right? Yeah. Yeah, go ahead. Oh, go ahead. I mean, you were first.
Sorry, is this strange metal reentrant even if the superfins are fluorescent?
Yeah, it is. That's going to be my last slide. Yeah. Oh, wait. You mean strange metal at high magnetic field?
Yeah.
Oh, yeah. Good idea for an experiment. Yeah. But it's really hard to. So you know, high magnetic field, you burn like $10,000 per hour on electricity. so taking a careful temperature dependence in that field is you need to write some grants for that, I guess. Yeah. Yeah.
So in my understanding, the whole cycle multiply, when phi equal to 2 pi.
Yeah.
It should be same with the phi equal to 0. But when I say your
Yeah, I mean, it's,
calculation,
I mean, again, there's some overlash discussion with Jonah, but like you see, it's not exactly the same, right? So the thing is like this is 2 pi here, and then you see like it's not exactly what you get at 0. Yeah. So it's not exactly. I mean, it's similar probably, but it's not exactly the same.
So because the high field, the high field influence.
Yeah. I mean, it's still there's still a magnetic field in this situation here.
So in what sense this is periodic? So what feature you see the same with 0 and 2 pi?
I mean, okay, so I think okay, if you zoom in on 2 pi here, the band is again super flat.
Ah, okay.
Right. I mean, this is probably what's shown here.
It's flat.
Yeah. So if you zoom in somewhere in the middle, it's kind of broadened and patched into Landau levels.
So another question is about the correlated insulator. So we claim that it's a multi-insulator, but is there any other signature except for the temperature dependence for the resistance?
Okay, I mean, oh yeah, right. I mean, so basically, I mean, for me, the biggest argument was that all the peaks appear at exactly integer fillings. Then, of course, there was in the beginning a debate. What is a Mott insulator? Why do we call it now correlated insulator? In the beginning it was called the Mott-like insulator. I think, but I think in my understanding, it is almost the same as a Mott insulator here, except that we have another degree of freedom as a valley, right? So we have a 4-fold degenerate system instead of a Mott insulator is usually like a 2-fold degenerate system, right? And appears to exactly how filling here. It's at also quarter filling and 3/4 filling. But I wouldn't. In my head, there's no like a major difference to a Mott insulator here. How do the topological bands play a role here? That's
Maybe just one insulator refers to anti-ferromagnetic state.
yeah. Okay, Mott insulator is always antiferromagnetic. Here we have a more complicated picture, right? But I think right. I mean, those are the differences. I mean, I guess when people say Mott insulator, they refer to the original paper from Mott in the 60s or whatever, right? And this was a two-fold degenerate system and antiferromagnetic state that forms there, right?
Okay, let's thank the speaker again.